Hello, everybody, and welcome to our webcast titled Calibration Process Control Meets Reliability. I'm your host, Matt Grant, Vice President and Group Publisher for Power Magazine. Before we start, I'd like to cover a few housekeeping items and talk about how to participate in today's webinar session. First of all, our speakers, as you can see, definitely want to be a part of this conversation, want to be an open conversation, and will not be talking at you. We'll be utilizing video during today's webinar. So you will see a live video feed of each speaker during the program. This presentation will last about 45 minutes, and we'll have Q&A segments halfway through the webinar, as well as Q&A will be reserved for the end. My apologies. At the left of your screen, there's an area where you can type and submit questions to the speaker. So feel free to send in questions at any time during the presentation. We'll try to answer as many as we can during the Q&A session at the end of the webinar. If you're experiencing any technical difficulty whatsoever, you can type that problem in the same area at the left of your screen, and our production staff will assist you right away. There will also be some live polls as well as a survey that we will push out at the end of the webinar that we highly encourage you to please participate in. This program is available for download, and you can access a PDF of the slides under Event Resources at any time via this live studio link. This webinar will also be archived on our server, and future viewing will remain free of charge. And you can use the same URL to reach the archived program as you did to reach the live program. A certificate of completion for professional development hours will be sent out via email to every registered participant who attends. So now I'd like to introduce our presenters. For today's program, we're going to hear from Chuck Boyd, Ned Espy, and Roy Tomalino. Chuck Boyd is the Business Development Director for BMEX Inc. and has served the past 10 years working with BMEX, managing the key global and strategic accounts, and currently strategic market development within the power and energy sector. Prior to BMEX, he spent 25 years in varying roles of software development, system implementation, and business development. He earned his BS for computer information systems. Ned Espy has been promoting and developing best practices for calibration management for over 20 years. He contributed to the Engineer's Guide to Industrial Temperature Measurement and consults on collaboration best practices and provides technical support to BMEX customers as well as the sales team in the United States. Roy Tomalino has been teaching calibration management for 15 years. He's taught on 4 different continents to people from over 40 countries, often referred to as a calibration evangelist. He conducts training sessions and provides technical support to BMEX customers. Before we begin, we would like to very much thank BMEX for underwriting today's program. Their generosity allows everyone to attend the presentation at absolutely no cost. So with that, I will turn the program over to our first speaker, Chuck Boyd. Chuck, take it away.
Thank you, Matt, and welcome everybody to our webinar today. I did want to plug our annual calibration exchange, or ACE. This year we're moving into the West Coast. We'll be in California. This year we'll have editor-in-chief and visionary Walt Boyes. He's got 40 years of instrumentation experience. He'll be sharing with us the dynamics and the changes to the automation industry, and particularly the workforce, and share some of his ideas of what to expect coming up in the future. Also, our Director of Engineering Services, Mike Urin, will be presenting some increasingly stricter audit requirements and focus on data integrity in calibration. Our own Ned Espy will be doing a deep dive on calibration periods, calibration scheduling. There's a lot of variables that go into that, and he'll be doing a deep dive on that and give you some guidance on making some good decisions there. And then this year, our hands-on workshop will be led by our subject matter experts, will be focused on pressure calibration and proper maintenance and procedures for those pressure type instruments. So you'll get some more information on this, but everybody is welcome to register and attend that. Our agenda today, we will focus on a reviewing where we are today with our calibration programs. Obviously, this presentation is going to be focused on calibration. We'll focus on not so much assessing where the calibration is today, but how we got there. Then we'll focus on talk about some important metrology concepts to just lay the foundation for the rest of the information that we'll be covering. Then we'll focus specifically on error tolerances or error budgets, and also those calibration intervals. We will then hear from Roy, who is our boots on the ground, and he's out talking with the guys that are actually having to maintain these instruments and can give you some feedback from what they're saying. Then we'll come back and look at the calibration program and what provide some low cost and high impact changes that anybody can implement today. And then we'll come back and look at some strategies, more higher level overall strategies, and then we'll have a demo of a soup to nuts calibration, and then we'll wrap up with some Q&A. I did want to have a poll question just to start up. We'd like you to just rate on just your personal opinion at your plant, or if you're over multiple plants, grade your current calibration program. And it's just school grades, A, B, C, D, or if you feel like it is failing, an F. So if you can respond to that poll question, that'd be great. We'd love to see where everybody is on that. So process control and motivations. First and foremost, utmost important in every one of our plants is safety. So people and the environment and then the equipment, that is first and foremost. But also there's going to be, we're all trying to make money. We're all trying to use these assets to generate a profit. So, you know, that control system also needs to consider, hey, let's minimize waste. Let's minimize any impact to the environment, of course. Minimize energy use or maximizing the output from our energy. And then also keeping production going, keeping the plants running, keeping the plants going, and maximizing that output. So to achieve this, we're getting more and more tight control as a requirement. Tight control means there's less variability in the process. So it can be run as close to the way that it was specified to run and maximize those profits. So just kind of an overall, this is what we're trying to achieve with this process control. So we can't control anything we can't measure. I know that's preaching to the choir here, but the measurement, the quality of your control is only as good as the measurement system that's supporting it. So that is, measurement can be the weakest link in the system. It doesn't matter how exotic or how much you spend on your control system. If it's not getting good measurement data from the instrumentation, that is a very, very weak link. So these control instruments are responding to the process, and there's inherent changes that is primarily due to disturbances in the process, but also changing requirements, and also there, hopefully not, but there could be some design flaws. The controller is the core of the system, but it is also dependent, and it partners with the sensors that are measuring the process, the different control elements in the process, and also the process itself. So a competent control cannot really be achieved by just simply putting all your resources into tuning the controller. So if we look at calibration and define calibration, calibration is real simple. If you Google calibration, it is going to say, just about everything is going to say the same thing. It is comparing a known measurement standard, one that you have a document or a certificate saying, hey, this is accurate. We know it's accurate. And you're comparing it to an unknown. And that unknown is the instrument under test. It's very simple, but can be quite complex at the same time. So the calibration program today, metrology is, it seems to be kind of calm on the surface, kind of like that duck in underwater. He's paddling like crazy. It has a lot of different disciplines in it. It is statistics, mathematics, science. It has a lot of different physics, quality control, quality assurance, chemistry, computer science, and it's all wrapped up in it, and you need to apply it with a little bit of common sense. So metrology is interspersed with everybody's job requirements, their job duties on a daily basis. Everybody, metrology touches everything, but it's really not really intimately understood. It's only by a few people. There's outside of nuclear, there is really rarely a defined metrology role at a plant. So most, if not all, of metrology knowledge is learned on the job. So with the lean staffing levels that we have today, these programs typically it's very common for these programs just to evolve out of expediency. The lack of a defined metrology role inhibits the development of a program that's built around metrology fundamentals. And you have a lot of different people. You can have a calibration program of 15 years old, and we've had 30 different people involved in it, and there's no consistency and very little metrology expertise applied to the program. So they just get by and just with what they need to do. So if you look at the minimal requirements for a calibration is, you use a standard to prove traceability, and you measure it, and you document it, and that's good enough. But it is calibration is also, there's a profit motive. So if your process is running as designed, it's going to increase your profitability. There's a lot more that can be applied to your metrology program or your calibration program that can reap a lot of benefits. So if we look at the calibration in an O&M context, you got an instrumentation and electrical manager, and he has a responsibility over a wide range of items. He's providing leadership in safety, and environmental leadership. He's managing a team. He's managing outside resources, working on projects. He's working on preventative maintenance, predictive maintenance, and critical repair activities. He's got a lot on his plate. There's more. That's just some of it. So when you look at calibration, it's kind of just a real small part of what he has to do. So it gets a very small amount of his focus, and all else being considered. So at a minimum, a calibration program, it needs to be calibrated on schedule. It needs to be documented, and unfortunately, that is typically just enough. So this, when calibrations are done in a context with a good metrology fundamentals, it can prove profit. It can show a good profitability, get more out of your process. That's what we'll be talking about today. So I am going to turn it over to Ned, and take it away, Ned.
All right. Thank you, Chuck. Appreciate you giving some ideas and thoughts about how people need to assess where they are today, and what kind of things should they be looking at for improvement. But I'm going to change direction a little bit and kind of get into some fundamentals. I want to talk about what really the basic things a technician should know, or management should know, what they're asking their technicians to do when it comes to making a good quality measurement. So let's move to another poll question. And this is a little busy on the answers, but in general, we'd like to know, what do you guys use for a pass-fail tolerance? Is it something really low, under 0.5%, or is it somewhere between 0.5% and 1%, or sort of a 1 to 2% tolerance, or something greater than that? And if you don't have an answer, we give you a couple outs here. But if that gets pushed out to you guys, let's see what you say out there. So if you don't know, I guess you can hit the F there. And so I'm seeing some numbers come in. I'm going to push this out. I'm going to give it a few more seconds here. All right, things are looking kind of interesting here. So I think if I push a button here, I'll give it a little bit more time. I just saw it do another shift. And let me make a note of some things here. All right, let me push this button, and it says they were sent to the audience, so I hope you guys can see it. But what was interesting is it looks like for those that have a tolerance kind of set, it's around either at the 0.5% to 2% window. It's very interesting that the largest response was other. And then I feel sorry for the technicians that are operating under 0.5%. That's a very tight tolerance. So it's kind of interesting where things are. So so let's move on. We'll kind of keep this in mind about especially those that answered other. All right, so getting into the basics, let's first talk about traceability and test ratios. So, you need to use quality equipment when you're performing calibration. And as Chuck said earlier, the base definition of calibration is comparing a measured value to a known reference value. So we're talking about the reference value part of this definition. And so when you're doing calibration, it has to be traceable. You need to have a pedigree showing that calibrator's in good condition and is making that kind of accurate measurements you need to run your plant. And traceability is typically, I almost call it a pedigree. But it's some kind of document showing that a higher level reference standard was used to check that calibrator. And here's some examples. In the United States, we have NIST, and I'm listing some other laboratories throughout the world. And within and under those groups, there's accreditation bodies. So again, in the United States, we have A2LA. BMEX is a Finnish company, so I'm showing our Finnish counterparts. So in Finland, MIKES is equivalent to NIST, and then FINAS is equivalent to our A2LA for accreditation. So I'm showing some logos here. Here's NIST, which is overseen by NAVLAP, and then here's FINAS. One thing, this little logo here, the ILAC, it's a mutual recognition agreement, and I think over 100 countries have signed it. So the idea with this agreement is that when you measure a PSI in the United States under NIST traceable measurements, FINAS will recognize those as in Finland. So just know that this stuff is going on, and as Chuck said, there's a lot of science behind calibration. And then here's this pedigree that I was talking about. So when you make a calibration on a process instrument, you're using a calibrator that's certified. That calibrator was certified by a reference standard, and then those go back to national standards and ultimately international standards. And one of the good rules out there, it's kind of an old military standard, is you want to have a 4-to-1 ratio. In other words, your calibrator should be 4 times as accurate as what you're trying to achieve in the process. So for those of you that are working under 0.5%, that means your calibrator needs to be like 0.1%, or even if you're down at 0.25%, it needs to be something like 0.05% of span or reading, whatever the ratio is, to get that good traceability. And then just to kind of give you an idea, this is for the process plants out there, the power plants. But in our lab here in Atlanta, our goal is to have a 10-to-1 ratio. We like to have our standards that check our calibrators to have like an extra decimal place than what our calibrator displays. And this is very difficult to do, but this is a goal that we try to achieve. So this is kind of some philosophy behind making a good quality measurement. Now, I want to give you some concepts. I want to talk about accuracy, which is, I put in parentheses here, a base component of error, versus uncertainty, which is kind of a statistical average of errors. So when you say, you know, how accurate is this calibrator, or how accurate is this instrument, you know, it's kind of a moving target. And you know, so here's a definition of accuracy where we're saying that it's the closeness of a measured value to the known reference value. And but notice these things that are missing in accuracy. There's other components of error. So accuracy is just one component. But you know, how linear is the instrument? How much does it drift over 6 months, over a year? Is there hysteresis? Does it measure differently when the signal's going up versus when it's going down? How repeatable is that measurement as you change? How about temperature effects? How's that instrument perform on a cold day versus a blazing hot day? Things like that. Also, how do you state accuracy? Most often, and you heard me say percent a little earlier, and I said, you know, the 4-to-1 ratio, and typically people look at a full scale value in our process world. But you may also consider a percent of reading, and then I've got plus adder here. This is sort of a base error. So if something has a percent of reading accuracy or measurement, there's usually some kind of basic base level error. And here's a little graph showing the two things. So the blue line is a 0.025% of full scale calculation for a 300 psi range. So if you take 300 times 0.025%, you get 0.075 psi. And then if we had a different statement, 0.01% of reading and 0.005% of full scale, that's the red line. So see how it has that base error at 0. It's the 0.015 psi, and then it moves up at a slope. So the point, I guess, of these two statements, the full scale versus the percent of reading and base error, is the red line is like twice as accurate as what's stated by the blue line. But in any event, the only way to compare accuracy statements is to actually calculate the engineering units that you're working in. So notice that this graph is from 0 to 0.08 psi. So to show, you know, to do a true comparison, you have to just use these examples and calculate to the engineering units that you're working in. So this is a way for you to interpret how accurate pieces of equipment are. So contrast that with expanded uncertainty. So uncertainty, it's really, there's a lot of mathematics behind this. And it's obtained by using a coverage factor or confidence level. So you maybe have heard of something being 2 sigma. Maybe in quality, you've heard of 6 sigma. So 6 sigma is all these decimal places out. So this is why this is like impossible to achieve. But when you're looking at making measurements, you're looking at data and you want to have some statistical backup to it. And so it's just, for this presentation, I'm not getting into any depth, but just think of uncertainty as a statistical average of all the components. So remember, on the previous slide, we were just talking about accuracy, but there's so much more. You know, how accurate was the reference standard that was used to help state that accuracy? That needs to have that 4-to-1 or 10-to-1 ratio. And then these other components get averaged in, if you will. And there's more than just this. So when you hear somebody state uncertainty, that gives you a much higher level of confidence in how valid the instrument is in making a measurement. All right, so let's talk about one other parameter or area for calibration, the different testing parameters. So one thing that you guys have to figure out is how often should an instrument be calibrated. The manufacturer might have some guidelines, but really you need to look at specifications. How stable is the instrument over time? How much does it drift? How varied are the ambient conditions? Is it in an air-conditioned part of the plant, or is it an area that's outdoors? And then how demanding is your process? And all this could be moot if there's some auditor coming in and looking at something. They may mandate that you test something on a regular basis. And of course, you need to look at what does that instrument cost you if it's not measuring accurately. So another parameter you have to figure out: what is the pass-fail tolerance? You might do what's called a criticality analysis, and I add this little comment here. So you guys that were doing 6-7% of you were doing tighter than 0.5%. That costs you in a lot of ways. You need to have more accurate test equipment. You need to have good gear to make those measurements, and you might need to go out more often if there's some stability or drift issues with that given instrument, in order to be confident that you're making that tight tolerance. So that's a message for management, that when you ask your tech to do something to 0.25%, just know that you're asking a lot. And then, what are your best practices within your, not just at your plant, but within your organization? How do you check a DP flow meter? There's got to be the best way, and maybe it's not what somebody like BMEX would say, or some consultant. It's like, what is the best way for your organization and at your plant? And know that things are getting better and better with today's digital instruments. They're performing much, much better than the old pneumatic days. But what I say is the only true method to determine the optimum testing parameter is you somehow have to collect some data and do some analysis and see how much your stuff is drifting, and then you can make some good judgments. So documentation, to me, is the only way to get a handle on this information. So, when we talk about a testing interval, there's so many variables, and the best you can do to start is to make an educated guess. So, focus on your critical instruments. Consider all these factors will help you determine what's critical, and then, if you can collect data, you can start seeing if there is drift. If the instrument's not drifting, you can back off on your schedule. If you've got a real tight tolerance, maybe you need to tighten up on your tolerance. But one thing I tell our customers is that not adjusting is a good thing. If you go out and the instrument's in pretty good shape, maybe it's not perfect, leave it alone. If you can catch it until it's way out, then you adjust. So if you're always adjusting, then you'll never know how much that instrument is drifting. And then you need to, if you're seeing inconsistency when you're collecting this data, you need to consider what's causing this problem. Try to see if you can get a handle on it. But the goal when you're looking at this information is try to distinguish from random error and systematic error. So random error might be ambient conditions, it might be the media, things that you can't necessarily control. But if the instrument is drifting and you're seeing a consistent change over time, that's something that you can do, that you can control. You can make adjustments to the instrument and bring it back to factory new condition. So just to wrap it up, test intervals should be determined by your actual failure rates, not what some manufacturer says or not what some consultant says. And here's an example. So here's a test that was done every 6 months, and it looks like the pass-fail was 1%. And after 2 years or more of data collection, look, the interval was changed maybe to 9 months, and the tolerance was tightened to 0.5%. And finally, and there still was no failure. An adjustment was made. It was brought back to true, same interval. Look at that same angles there. And then finally, we drifted out. We doubled the interval maybe here. And in this example, maybe you went from a 6-month interval to close to a 2-year interval. And you made this kind of change with a lot of confidence. So if you have good equipment and a good metrology program, as Chuck alluded to, this is the kind of thing you can start getting into. All right, so I'm going to turn this over to Roy, and I got to tell you, I'm just going to warn everybody, this is the first time Roy has ever had a slide.
What? I'm not exactly sure how to take that. So thank you so much, Ned. I have a slide, really? What? Oh, serious? Okay, we did the pirate. Okay. Roy Unleashed. You know what? Ned actually wanted it to say something like Roy's rant or something like that, which I guess is pretty accurate. But one thing that I want to point out also is 2 days ago, I was driving through Castle Rock, Colorado, up into Denver, and it was a blizzard. 2 days ago. We are not in winter mode here anymore. So I'm going to show you my personal gear. This is what I do for calibrating in cold temperatures. We didn't ever talk about safety. This is our little safety minute with Roy. You want to make sure that you have your proper safety gear. So this is my personal hard hat, and this is my personal floppy wing hat to make my head a little bit warmer than normal. So now that we have safety out of the way, let's do this. We took a poll earlier about how's your calibration program doing. Let's push those results out if we haven't done that already. Survey. So how did everybody do? How would you grade your plant's current calibration program? So, what, 6% an A, a 45, about half of you a B, about 40% a C, and then a D and an E. Now, I have to tell everybody, the only time I ever saw an A in school is when I was absent. Yeah, anyway, so B, C, B and C is the most. I'd be curious about the ones with an A. And one thing that I want to point out here is that there might be some trepidation. You don't want to be the guy that says, all right, our program is a D, or it's an F, or it's a C, but you know what? It said, actually, it's really bad. It really is an F, but I don't want to say it out loud. So with that, one thing that's pretty common is that to the customer sites that I go to all kinds of, every different customer that actually performs a calibration. It doesn't matter what country I go to or what continent, it's similar. And if you don't have a good grasp on your calibration program, everybody thinks they're the only one that is struggling. And if you're struggling with your calibration program, it's okay. There's no shame involved with that as long as you are able to move forward. So here's the point of my unleashed moment here is that in order for your program to be successful, whether or not you have the best products, the best calibration setup in the world, if you don't have buy-in from the top down, you're not going to be successful. And in some of those cases, it means that you need a champion, somebody, a technician. Maybe they're a lead tech, but it's good if they're respected, and generally they're respected the more they're put into this role. But in order for you to be successful, you have to tell everybody why. You have to tell them why they're doing the change. And if we look at change is difficult, even if you're doing something that's better. If you have, all right, you're a technician, or you've been managing your calibration group for 10 years, but there's something new out. But you know what? Change is hard. But the change of staying the same has to be greater than the pain of changing. Let me say that again. The pain of staying the same, the status quo, must be greater than the pain that's associated with the change that you're about to bring forward. Now, in here, I have the most amazing calibration solution right here. And if I, let me, just a minute, I'm gonna, okay. It's right, it's it. No, this is, here it is. This is it. This is the most amazing solution for your calibration issues. It's right here. And you know what the secret is? It really doesn't matter what's in here. It's that we communicate this from the top down and everybody gets bought in to give this a shot. We all need to give it a chance. There needs to be a champion, and you're not in this alone. You gotta have somebody to help you. And with that, my rant is done.
Thank you, Roy. I guess that tosses it over to me. It's always entertaining, and go get a cup of coffee. So I'm going to talk about real quick on some of the things that we can implement today. Very easy to implement, low cost. It just takes a little bit of discipline. But if you look at how maintenance is scheduled, you know, we're planning for an outage and months, years in advance. We got a lot of different moving parts. So adding extra steps to the calibration program is counterintuitive to that. So, you know, did I do that? I think we advanced the slide by accident. It's not like labor savings. You can't, it's very difficult to quantify improvements to the process and process control in order to make business decisions on investing in making change. So here's some areas that we can implement today. Doesn't take a whole lot of effort. It is going to require some change, but they can have it can build a good culture of metrology and good calibration practice. So first, measurement tolerance and pass-fail determination. So tolerance, every instrument needs to have a tolerance or an error budget. This does not, please don't base this on the accuracy stated by the manufacturer of the instrument. It should be a combination of what the process requires, the criticality of the instrument, the environment that it's used, to define a tolerance for each instrument. And it's okay to have an overall tolerance, but each instrument needs to be looked at. The second part of that is being able to determine the uncertainty. Tolerance is required in order to develop an uncertainty budget as well. Pass-fail determination is actually calculating using that tolerance. Let's see, are we within tolerance or not? So that should only be done by calculating the error based on the tolerance. So I think a lot of, in the survey, a lot of errors are based on a percent of span. It can be a percent of reading. It can be an engineering unit, such as a milliamp. But it requires some math out in the process for that technician to determine if we're within a pass-fail status. So a lot of these, as these programs evolve, it is relegated to a technician's gut feel. You know, they've been doing it a long time, and they say, well, that's it within tolerance or not. The problem that presents is that it is recorded in perpetuity as a passing calibration when in fact it really wasn't mathematically calculated, and it can present problems. The operators are making decisions based on this measurement. So assign a tolerance and then actually calculate what that error is so we can compare it to the tolerance. Second is a test strategy including hysteresis. Hysteresis is the difference between a response to an increasing input versus a decreasing input. So a lot of our test strategies, you know, 0% and 100% is absolutely terrible. It's almost useless. 0%, 50%, and 100% on the scale is a good balance between practicality and feasibility. But hysteresis is going to show, if you go up the scale and back down, hysteresis is going to show you typically if there's a difference between increasing and decreasing inputs, it is a friction on a sensor somewhere, and that says that that instrument is about to fail. It needs to be corrected or replaced. You'll never find it without hysteresis. So test strategy up the scale and back down. Identify hysteresis. Third, maintaining acceptable test uncertainty ratios. Ned discussed test uncertainty ratios. That's why we have to define a tolerance in order to understand the test uncertainty ratio. So what this is every measurement is just a snapshot in time. It's an experiment. So every measurement can be different. A test uncertainty ratio gives us a window of if it's within tolerance or not. Each measurement has a test uncertainty ratio, but we make it real easy. Typically, the industry standard is, let's look at the test uncertainty stated by the measurement standard. So your calibrator has an accuracy statement, and we can use that. That accuracy needs to be cannot be more than 25% of the measurement we're trying to make, which gives us a 4-to-1 test uncertainty ratio. One of the challenges is that these standards that they're using in plants today could be 10 years old, where 2 years ago we had a control system upgrade with all brand new instrumentation, and our instruments could actually be used to calibrate our measurement standard. Securing information assets, our fourth item here. All of these need to be, system needs to be, information needs to be documented, easily accessed. The calibration specific data and applying metrology to our program needs to be documented and stored in a database. Data is our most important asset, and protecting that data is critical. And this also mitigates some of the issues with people moving on. Somebody's that's been managing a calibration program and moves on. All of that knowledge is gone. And so if we can secure that in a database, also that addresses somewhat our phenomenon, a global phenomenon of our aging workforce. So get that data secured and owned by the business, and not walking out the door with folks leaving the business. So I'm going to we're going to have another poll question, and I'll flip it over to Ned. Ned?
All right, thank you, Chuck. Appreciate that good information. I think we're running short on time here, but let's ask this question real quick. So wake up, everybody. This is a little different than what we've asked before. How would you describe your calibration management program? Are you using some kind of computerized database, or do you just drive it through a scheduler like a CMMS and maybe scanning paper to put against a work order? Or C would be paper forms that you just file in a cabinet, or good old index cards going way back. There's still people doing that. And if you don't have a formal plan, maybe that's an answer. So if you all would chime in with your answers. I see them coming in now. Looks like we've gotten good percentage of customer or viewers here to respond. And let's send these results to the audience. Let's see. I think we're close enough here. So it's kind of interesting that the majority are using paper forms, and that's not surprising. And my challenge to those folks is whoever looks at that paper, I guess if you get audited, you can try to find it and pull it out. So more and more we're seeing people move to the A and B. They're starting to try to get paperless, so they're scanning the documents collected and then attaching them into a electronic history. So it's good to see 22% of you out there are using some kind of database, and then maybe the group in the lab that have no formal plan, maybe we're inspiring you today. Okay, so moving on, and I'm going to go through these slides very quickly, but one thing I want to push is that ISA does have some nice guidelines. Last year, a new recommended practice was published. It's Recommended Practice 105, and the title is Management of a Calibration Program for Industrial Automation and Controls. So, so this is something really brand new, and it was authored by some real experts in the industry. In fact, Leo Staples, past president of ISA, is with Oklahoma Gas and Electric, very knowledgeable on maintenance and had a lot of input on this. And here's a link where you can go If you would like to purchase this, it has just a lot of good things, and this is kind of an overview comment from the guide. But if you don't have a program, all bets are off. So, and God forbid something would cause some kind of unsafe action. And I'm not going to read all these off to you, but here's a bullet list of some things that you should consider in your calibration program, and look for ways to become more efficient and do things more accurately and with better efficiency. So ideas of looking at a loop rather than individual instruments, and taking advantage, leveraging your smart devices, which are much different than the old pneumatic devices. Don't use an old pneumatic type approach to a smart instrument. So that's one resource you have. You can also sort of self-audit. How do you execute a calibration today? So here's a little workflow. You do an as found. If it passes, you check it in and it's approved, and maybe you file your paperwork some way. But if an adjustment has to be made, then you do an as left test. If it's okay, it's kind of similar, but you've had a deviation. If you can't get it to adjust, then how do you issue a repair or replacement work order? So these are kind of things you should look at your program and look for efficiency gains. And as Chuck said, you need to establish procedures and follow those procedures. And doing good documentation is important. And I know you can't see this document, but you've got database information, you've got event information, procedural information. This is traceability, what was used to make the measurement. Here's the actual data. Here's a graph. You can see the as found was maybe at an angle and the as left was left perfect, and then who performed the calibration. These are all good examples of proper documentation. And this next slide it actually came from an SIS presentation that we did, but I feel like it applies to any type of calibration documentation. So, you need to be consistent. You want things to be relevant, repeatable. Education is a key component. Roy was talking about getting buy-in, and one way to get buy-in is to get everybody properly trained and on the same page. And your goal is to get high quality data. So when you're going out to make a measurement, it needs to be of the best quality you can make it. And so instead of writing things down, get it in electronic format as soon as you can. And here are some benefits. This shows a paper-based system versus an all paperless system. And you can see just because there's less steps, there's less chance for error. Getting things in electronic rather than filing it in a file cabinet. You can imagine there's just lots of benefits. So, and then once you get it in electronic format, then the reporting is what pays you back. So, I think that kind of concludes our presentation, other than we want to show you a demo. But before we move to the demo, another poll question, and we kind of are calibrating our audience. We asked the same question at the beginning. How would you rate your plan? And Roy pushed it out where you could see the results. Would you mind reassessing and giving the same answers to fine, but we want to see if we moved anybody from their earlier analysis. So let's take a look. I don't see anything coming in yet, but if you go ahead and give yourself a rating, A, B, C, D, or F. So just like going back to school. So Roy said he never got many A's.
Well, I did, but they were for absence.
Oh, A for absence. Okay.
Yeah.
So I'm not seeing, well, there is one kind of shift. Let's see. This is kind of interesting. I'm going to go push this out. I'll let somebody else maybe push it out. Let me see if I can push them. And if you can see these results, what's interesting is some of the people that gave themselves a B or C moved themselves to a D, and some of the people that gave themselves an F maybe moved to D. So maybe we had, and the A's, well, I don't know if I pushed that out too soon, but the A's dropped down to 2%. So that was very interesting. Well, that'll be some good digestion for us here at BMAX. So thank you for doing that. All right, so I think it's time to move on to.
So we're going to do the demo next. Ned, thank you so much. And this demo is actually pre-recorded, but I wanted to let you know I did this actually 2 days ago, but it was 24 minutes. We condensed it down to 11, and everything that happened is real, and I wanted it to be grabbed. And if you have an interest in seeing everything that occurred, then I think we can probably make a link for that. But the key thing that we're doing an as found, and then we do an adjustment through the communicator where I do a trim, and that part is completely skipped. I wanted to fast forward through it, but we weren't able to do that. And then the as left is done. But just know that there was a trim that actually occurred in the middle. And here we go. Welcome to today's calibration talk. We'll be calibrating a pressure transmitter. What do we got? Well, we have a Rosemont 3051C differential pressure. We have a high side over here, a low side over here. The low side, I have the vent opened. Pressure-wise, we've got a pressure pump. Our pressure hose itself has 3 legs on it, so we have 3 of these, and then there's a union in the middle holding everything together. So now we have our 3 connections. We'll take one connection here. These are all designed to be finger tight and not have to use tools on them. I'll do one of them on the I'll do one on the calibrator itself, and the final one on the pressure pump. So on the calibrator itself, let me bring up a viewer so you can see what's going on easier than this camera. Now, we have this transmitter, we need to build it. We'll go to documenting calibrator, and I'll click on here so you can see what's going on. Now the yellow star is how we create something new. And there's a secret button here on the top left. I'll do get mapped values. This will fire up the HART communicator and allow us to build a tag. It'll pull over the input range, it'll pull over the output range, the tag name, the serial number, the make, the model, all the core info needed to perform a calibration. And this is where we come to the key point of how do we do this calibration? Well, number one, if this is a 0 to 207 inch of water transmitter, that means at 0 we have 4 milliamps, and at 207 we have 20 milliamps. So we're connecting here, which is correct. I've got that over here. And then we're also connecting right here, which is these 2 guys, and I'm connected there as well. Loop power is on. I'm going to hit the check mark, and I have some pressure applied right now. So let me just open the vent, and I don't need to re-zero it. Let me just start it. Counting down, we have 0 in, and we want 4 milliamps out. So we have, right here it says negative 0.627% of span error. Now we'll close off the vent, and I will pressurize this to get us into the 25% area. And I'm just doing a slow squeeze on that. I could be doing the fine tune knob. So now we have, okay, so now we're doing the middle test point. Take it up there. Whoa, I totally overshot this thing. So we could bring it back down again, but the real way to do this is to bring it back down far below and then bring it back up again. Otherwise we remove any hysteresis in our measurement. But I can accept this right here, and this is still a valid measurement. At 162.27 inches of water, we're getting 18.2486 milliamps. And I'm just going to accept this right here. I'll choose force accept. It's outside of our little gray bar that we were aiming at, but that's okay. As long as it doesn't violate any of our calibration policies or procedures, this is still a valid measurement. This also is a good example if your final test point is a pressure that you cannot simply achieve with the pressure pump that you have. Or maybe you have a vacuum and you can't go low enough. You can't hit absolute zero. Well, there's not much that can outside of a space laboratory. There's a couple options, but then they start counting actual air molecules. Final, on the bottom right, we're aiming for 207 in and 20 milliamps out. So let me bring this up. So, and I'm letting it stabilize here. Let me just set the pump down. I do like to do that so that we know that it's actually stabilizing as best it can. It failed. So this means I'm not a good calibration technician. No, that's not what that means. This means that the device itself failed. As long as all of your connections are set up and they're good, this is the transmitter that failed and not you as a technician. All right? So from here, let me move this out of the way. If I arrow down, I can put a note in here. I could arrow down again. Wow, so this thing is all over the place. It failed on the bottom and it failed on the top. And everything red here is where we had a failing number. And then our environmental info, I'll just leave it the way it is here. Let me save it. Now this is ugly, but we can fix it. So let me do as found, check. All right, now we're ready to do our as left. Let me vent my pressure. But what I need to do is do an adjustment. So we need, I just need to figure out where to make the, well, okay, actually this is a heart device and we do it through the communicator. So to fire up the communicator, we bring up the secret button. It's also called the magic button, whatever. The real name is the menu button, but I like the magic button. We'll go with that. Upper left, magic button, start communicator, please wait. Cue elevator music. All right, we're done here. Hit the X. Now we're back in calibrator mode. You know what? We still have pressure on here, and we can see that the error, it is perfect on the end. But we're going to start off at the lower end. So I'm just cracking my vent, and we'll see it go back down. So my pressure pump is vented. We have 0 in here. There's no need to do a re-zero. I could, but let me hit start. Now we're in our gray bar. We're in our target area, so we have a 5-second countdown. Now the next test point is 51.75 inches of water in and 12 milliamps out. So let's do that. Closing my vent. And I could use the fine-tune knob, but I learned this from some guys in a water treatment plant in LA. These guys have been using these pumps for, man, over 15 years. And I would have gotten close and then I would have started using the fine-tune knob, but kudos to you guys. Taught me how to use a pump better. So you can just be very slow and deliberate even with this handle. And then I never even used the fine-tune knob unless I actually end up messing up. And I'm getting in here somewhere till I went over a little bit by about 1.5 inches. And it doesn't matter because we're measuring the output against the input that it's seeing. So we're seeing a live error across the top here. So I could overshoot it or I could undershoot it and I could force accept it. It's still okay. So I even went up a little bit high, and that's my tendency to take it a little bit high in case I do have a little bit of a leak, that it'll just leak down and then hit the number that I want. Now I'm resisting the urge to bring down the fine tuning because wherever we are in the number, so this one passed, our actual error when we set the pump down is 0.021% of span in a negative direction. The significance means that this error equates to 4.2% of our error tolerance allowed. And our error tolerance allowed was 0.5% of span. So arrow down again. I'm not going to bother putting in notes here, but here's the graph of how we left it. These are the raw numbers, so we're really good on our zero and our span, and the numbers in the middle, we don't really have an ability to trim on those. So arrow down again, those are the environmental conditions. I'm going to save it, combine it with our previous as found. I'll do as left, that's good. Now we're done. Now let me do this. I'm going to close this out and actually unload it so we have a complete document. And I'll fire up CMX, the calibration software. Here's my test result. So this is what it looks like. From the red is from when we started, and the green is how we left it. So if you're being audited or you need to give this info to a supervisor or maybe quality, I would do this. Right click it and go to print certificate. Let's do a preview. The preview lets us look at the final product, and so I created this from scratch, so we have some fields that are missing on here, but here's our graph. But now let me zoom in so you can take a better look at it. This is a square root, 0 to 27 in, it's 4 to 20 out. We had a 0.5% of span tolerance, and it also shows us what standards we used to perform this calibration. And a calibration is comparing what you're doing against a known standard. That's what calibration is at its root. You are comparing a known value against the standard. We used this MC6 for the input, this one for the output. Here's our graph and the raw data and who it was calibrated by. So it was calibrated by Roy. So there you go. Calibration complete.
Great. So thank you all for the great presentation. We've had a number of questions come in from the audience during the course of the program. So we are going to answer a couple since we're over the hour here. And then after the presentation, the BMAX team will be following up individually on all the questions that we can't get to, as there were a lot of great ones following this program. So let me start with the first question for you guys. How do you identify drifting instruments?
Well, maybe I'll take a stab at it. Roy, you can chime in, but I would say technicians have a gut feel. They know stuff is drifting. They know that stuff is pretty reliable. But my part of the presentation, my opinion is that of your critical instruments, you need to document those and see what the actual drift is in your process, in your plant, under your conditions. Because depending on what part of the country you're in, the same instrument might drift a different way. So if you're way up north, harsh cold could affect it one way versus down in Florida where you have really nice weather, or California.
Yep. And so Chuck mentioned that you have to measure it to quantify it. So you have to do measurements periodically for you to notice if it's drifting up or down.
And that drift will be based on how much error the instrument is getting. If you're getting more and more error, that's going to show that drifting further and further. So calculating the error, compare what error you had the last time you calibrated it. That's going to show you your drift.
Yep.
Great. Thanks, guys. And so last question here, out of respect of everyone's time in the audience, can you tell me the best calibrators for flow, pressure, and temperature elements in the manufacturers?
You're saying the best measuring instruments?
Best calibrators.
Best calibrators. Really?
Well, I would have to say that you want a calibrator that is going to be very functional, very usable, easy to use, and accurate. We got control systems and instrumentation is getting more and more accurate. Processes are more and more tight. So you need to have a calibrator that is also going to evolve with higher accuracy.
So that's a good point. I just want to say this, that if you're doing all three of those things, you have flow and pressure and temperature, generally on a calibrator, you can get pressure and temperature, and flow, you can do a differential pressure because that's basic pressure. But flow, you're going to be hard pressed to actually find a portable calibrator to calibrate flow because it's a quantity based thing, and you probably have to send it off to a lab. If you do want to calibrate flow, you can put like a 50-gallon drum and run 50 gallons of product through it, and then see if it shows up as 50 gallons on your actual result.
But check out BMX.
Yeah, check out BMX. You kind of have to work backwards. I think Chuck and I kind of touched on it is, once you establish your tolerance of what you're trying to do in the process, it'll point you to the kind of accuracy you need in the calibrator. So if you have a tolerance that's kind of, 4%, 2%, something that's a little higher, maybe you just need some good test gauges. They're not, but one thing that's true in the calibrator market is the more accurate something is, the more you pay. So a good deadweight tester, for example, is $20,000 or more. And that's what we use in our lab to check our pressure standards. So it all kind of balances out, so you need to do some analysis, and it all comes back to what do you need in your plant? And you almost can back into what are the possible calibrators we could use.
Yeah, just one final point there. Whatever level you're at, whether you're A, B, C, D, or F, just improve. Do better of whatever you're doing, but just know that you're not alone and get help. I guess you could take that a couple ways.
Well, just one more note on that, on securing those information assets in a database that you can access. It establishes that benchmark where you can show improvement that Roy is talking about. Well, you need to establish a benchmark so you can start recording how much improvement.
Excellent. Well, we have officially reached the end of the program. So as mentioned before, we're going to do our best to have the BMX team address further questions individually by email following the program. Also, we ask that everyone in the audience please stay on for just a few extra moments after the conclusion of this presentation to participate in a very short, quick survey. Thank you very much once again to BMX for underwriting today's event. Thank you, everyone in the audience, for attending. So we hope you will benefit from today's presentation. Have a great day.
Cheers.
All right, Matt. Thanks a lot. Appreciate it.
Yeah, cheers.